too long ago, I made a video on Pascal's triangle, and I mentioned that it is closely related to the binomial theorem. So I'm excited to bring it all together today. As always, there's never any pressure here. I do hope that this is helpful and a nice, encouraging, loving, relaxing way to review or study. But of course, if you want to just sit back and zone out and relax, or even use this video to fall asleep, that is perfectly okay with me. Right here, right now, it doesn't matter what your relationship with math is, whether you like it, hate it, somewhere in between, whether you think you're the best at it ever or the worst at it ever. I guarantee you neither extreme is true. So let's just bring the pressure and the stresses of the world down. Let's just lay them down for right now, Decaf style. And let's just enjoy this moment for what it is, okay? Okay, so let's start with writing out the formula. If you happen to be learning this in algebra, most likely you won't have to know this particular notation, but I think it's cool to see it all in one place anyway. And then we'll focus on what it means and look at some patterns, okay? So, first of all, if we have x plus y to the power of n, this equals sigma of n choose k x to the n minus k times y to the k, as k goes from 0 to n. So this is our main binomial expansion formula. So let's break this down and look at what it all means here. So on this side, this is our binomial side. We have x plus y, so we have two terms that are separated by a plus. It can be plus or minus, but if it happens to be minus, you can treat it as if we're adding a negative number. So plus just keeps it general here. And so this is our binomial, two terms, and specifically binomials have to be polynomials that have two terms, and there are specific rules for the variables and the exponents for polynomials. So all we have to know for now is basically that this is indeed a polynomial and a binomial. So we have two terms that are separated by a plus or a minus raised to an exponent. And what we're basically doing is expanding this. So this exponent here, n, has to be a non-negative integer. So we can start with 0 and then all the positive counting numbers. So 1, 2, 3, 4, 5, etc. Okay, so whole numbers and non-negative whole numbers here. So that's n. So we're basically taking these two terms and raising it to an exponent, and this expansion, so this side tells us how to actually multiply that all out. So this doesn't necessarily look like a bunch of sums of terms, but this part is what makes it a sum. The sigma is adding in between everything. So what are we actually adding? Well, that's this part. So when k equals 0, I do this. So note that this n is the same as this n. So if I do x plus y raised to the 6th power, this is 6. This will be 6. All of the n's are 6. Okay. So I start with k equals 0, and this is the n choose k formula. So this is from our Pascal's triangle video where I defined this, and we can work with factorials more too down the line, but this is n factorial divided by n minus k factorial, and if you've done some combinatorics or some probability, this might be familiar to you, but otherwise you can just plug into this. And note that if you happen to get a 0 factorial anywhere, that 0 factorial is equal to 1 by definition. So here we have n choose, and you start with k equals 0 here. So you do n choose 0, and then x to the n minus 0 times y to the 0. So you just plug in 0 everywhere you have k, and you get this term here. So whatever, you clean that up. And as a little spoiler alert, that will actually end up being x to the n for the first term always. Then the next thing you do is go up 1, so k equals 0, and then k equals 1. So the next term will be n choose 1 x to the n minus 1 times y to the 1. And so that's your next term, and then you add, and then you go up one more, n choose 2 x to the n minus 2 y squared, and you add that. So all of these, as you take incremental values for k, become one of the terms in the expansion, and you add all of them until you get to k equals n. And also, spoiler, that last term is going to just clean up to be y to the k. Rather, y to the n, sorry. And so, in between, you have all the other terms, and that's why this ends up being an actual expansion. It's the sigma part, it's the sum of each of those that makes it an actual expansion. Okay, so let's actually build some intuition there, because it's a lot to say out loud, but there are a lot of patterns that are related to this, which is just, this is the cool part. So, first of all, I'm going to highlight the fact, I'll just let you know now, that right now we are talking about expanding x plus y, these two terms, as a binomial. But the reason I highlight that is because there are some applications of this in algebra, so you might use this expansion but use different terms for x and y in different examples in which it's not a binomial right away by the strict definition of binomial, but you can still apply this idea and basically just substitute these two pieces for x and y here respectively, depending on your actual given values. So we'll do some exercises with that later on, but I just wanted to point that out. So this definition here applies specifically for this form, something plus something to the power of a non-negative integer. Okay, so let's look at a pattern here. First of all, let's see what happens when n equals 0. So this is kind of like our first base case. It works, and it's not really that interesting, I think, because if n equals 0, then we have x plus y to the 0, which is just going to be 1. If x plus y, in this case, it's truly a binomial. In other words, x plus y is not going to be 0. Otherwise, you have 0 to the 0, which is kind of up for debate. But otherwise, anything else to the power of 0 is equal to 1. So it just is what it is. If you plug in n equals 0, then there's not really a sum because k equals 0 here. And it turns out that you'll have n choose 0, which is 1. 0, and then you start with k is 0. This is x to the 0, which becomes 1. And then you have y to the 0, which is 1. So you have 1 times 1 times 1. And so it's just 1. There's only one term, so it's not really much of an expansion there. But the formula does still work. If you do n equals 1, then we have x plus y to the 1 power, which is just x plus y. Anything to the power of 1 is itself. So we have x plus y, and I'm just trying to show the intuition here and the pattern, so we're not really writing this all out at the moment, but we'll come back to that. So if we do n equals 2 here, so we have x plus y squared. This might be a formula you are required to memorize in algebra if you took that, or if you're taking that. You might just be expected to memorize this shortcut. It's x squared plus 2xy plus y squared. Otherwise, you can just do this longhand, x plus y times x plus y. So, as you increase by a power of 1, you're just multiplying by another factor of x plus y. And if you want to work this out, you basically do FOIL. So first is x times x is x squared. Outer is xy, inner is yx, last is y squared. And because we're working with real numbers here, x times y is equal to y times x. So you can combine like terms and get 2xy. So that's where this comes from. If you want to slow down and review that, we definitely can, but I've made a video on this before, I believe, so, but we can always come back and practice. Okay, so let's continue to n equals 3. So if n equals 3, we would have x plus y cubed. And this might be another one of those formulas that you are required to memorize in algebra. If not, don't worry about it. If you were to do this longhand, you basically take the n equals 2 case, so what we had here, and multiply by another x plus y. And don't forget parentheses. But the thing is, if you multiply that all out, you have to multiply every single pair, and then combine like terms, so it gets quite tedious. And it gets exponentially more complicated. Get it? Exponentially. So basically, I'll just write this one out because I do know this one. And I just want to highlight the pattern here, so it's good to see it all out. But this is basically what we're doing. We're taking increasing exponents of x plus y, and these are the expansions on this side. So you can see that we have sums of different terms here. Some being plus this, plus this, plus this, plus this, etc., right? So this is our shortcut, and right now it's not too bad. For n equals 3, we have 4 terms, so it's not too bad, but this gives us a methodical way to expand out something much more complicated and time-consuming, such as x plus y to the 10th power, for instance. If you want to just sit there and do x plus y times x plus y times x plus y 10 times, it'll take you quite a while. So at least this gives us a sense of what the terms look like here. So how do these two relate? Well, let me highlight this pattern here. Let's look at the coefficients, the numbers that are in front of each of the variables. So here at the top we have 1. There's not really a variable here, so we'll just leave it like that. In front of the x we have 1 times x. Whenever there's no number in front, it's just default 1 because 1 times anything is itself. So we have 1 here, and then 1 times y there. We have a 1 here for x squared. We have 2xy, and then 1 y squared. We have 1x cubed plus 3 this stuff, plus 3 this stuff, plus 1 this stuff. So are you seeing where I am going with this? There is this lovely pattern that seems to arise. How very interesting. So if I write that, I have 1, and then 1 and 1, and then I have 1, 2, and 1. Curious, 1, 3, 3, 1. That looks very familiar. It looks like this triangle. So the next row of this, since I watched Decaf's last video, this would be 1, 4, 6, 4, 1, where you add these two terms to get the next. 3 plus 3 is 6, 3 plus 1 is 4, and I have 1s on the outside. Well, it appears that the elements of each row correspond to the coefficients of the terms of our expansions. So for n equals 0, row 0, I have just 1. 1, 1 is for 1x plus 1y. 1, 2, 1 is for 1x squared plus 2xy plus 1y squared, etc. And that's because we talked about each of these numbers in Pascal's triangle, and how they correspond to the n choose k, depending on your nth row starting at 0 and your kth element going from left to right starting with k equals 0. And then you can go term by term there. So the n choose k is actually right here. That's the coefficient. So that's the pattern for the numbers in front. But what about the actual variables themselves? So there is a pattern here as well. For starters, for the first one, it's just x to the 0. There's nothing to do there. It's just 1 at the front. But as you continue here, if we have n equals 1, it's x to the 1, y to the 1. But let's start with like this n equals 3, 1, because that will start to highlight this pattern. If you look at this actual formula here, so this is the coefficient part, what we're basically doing is we're starting with k equals 0. So this goes away, this is 1. So we start with x to the n. So in the n equals 3 part, it's just x to the 3. If you're doing n equals 5, the first term would just be x to the 5th, etc. Okay, if you're doing n equals 10, the first term is going to be x to the 10. Then what we're doing is we're decreasing by 1. So when k equals 1, you're doing x to the n minus 1. So you're decreasing the exponent of x by 1, and you're also increasing the exponent of y by 1. So the next one would be from 3 to 2 for the x part. So it's x squared, and then there's no y in the beginning here, but you increase y by 1 here. So the next term will be x squared y with the coefficient of 3 in front. Then the next term, so you do plus for the sum, you take 1 less for x, so from 2 down to 1, which is just x, and then you go up 1 in y, so from y to y squared, and you still have another 3 because it's 1, 3, 3, 1. And then for the next term, you go back down to 1, and you go down by 1 for x, so from x to the power of 1 to x to the 0, which is just 1, it goes away, and then y squared goes up to 3. So if you're looking at the x terms, you go from 3 to 1, 0, and if you're looking at the y terms, you're going from 0, 1, 2, 3. Isn't that cool? Okay, so now that we already have the next row of Pascal's triangle, we can actually continue this pattern for n equals 4. And this is where it'll really start to save us time. And remember that these numbers come from, the actual pattern of adding the two adjacent terms to get the term below for the row below. But you also know that it's n choose k, so this is 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4, based on this formula for factorials. But since we already have these expansion. So 4, we decrease the exponent on the x by 1, so it's x cubed, and add in a y because there's y to the 0 here, this is y to the 1. So we decrease x exponent by 1, increase the exponent on y by 1. Then we have 1, 4, 6, x decreased by 1, so 2, increase the exponent on y by 1, so from 1 to 2. And then we have 4 again, so 1, 4, 6, 4. So decrease x by 1, the exponent of x by 1, and increase the exponent of y by 1. And then lastly, we have y to the 4th. So you can see here we have 1, 4, 6, 4, 1. Then we have x to the 4th, x cubed, x squared, x to the 1, and x to the 0, which goes away. And then you start with y to the 0, y to the 1, y2, y3, y4. So counting up for y, counting down for x. And that's how we get this entire expansion. Remember, we're adding for the sigma, sigma, sigma part. So you can do this for n equals whatever you want, as long as it's a non-negative integer, so whole numbers only. And that should give you a general first idea. So what I was saying about algebra and how sometimes you end up just applying this formula, but you might not actually be working with the true binomial. I'll show you an example. So let's say you have the two terms, but you have like 1 over a minus the square root of 7b to the power of 5, something like that, and you want to expand this. Well, you do have two terms here and here. It's separated by a minus, so you can treat it as a plus negative if you wanted to. Just make sure you put like a parentheses, but you can treat it as a term and another term. And you can treat it as though it's a binomial, so you can still use this. Just make sure every time in x you put parentheses and do 1 over a, and every time you have a y you put parentheses and you do negative square root of 7b, and you use the same exponents, and then you do algebra to clean it up. This is not strictly a binomial by definition, but you do have two terms, so that's all you really need to do. The rest is just an application of algebra. The reason I want to point that out is because in this case, when you truly have x plus y as a binomial, you might notice patterns like the degrees, like here x squared and y to the 1, that adds up to be 3. 1 plus 2 is 3, y cubed, so the powers always add up to be 3, and that's just because n minus k plus k equals n, because the k's cancel, so you're just left with n anyway. But that's not necessarily going to be the case if you borrow a and b here, just because the degree of this a is -1, it's a to the -1, and this would be b to the 1/2. So a power of 1/2. So when you raise that all to the 5th, it's not necessarily going to satisfy the same type of properties that you might notice. But that's okay. There's no rule that says it has to. I'm just saying that sometimes you have applications like this where it is the binomial theorem. You might recognize that you have two terms, and then you just plug in this formula. But sometimes your actual x and y might be more complicated. Or for that matter, you can technically, it's very tedious this way, but for that matter, if you happen to have like a plus b plus c to the power of, let's say, 4, you can technically pretend that you have a plus b is x. So this is even weirder to think about, but you can pretend a plus b d or something, and then do the binomial expansion with d plus c, but everywhere you have d or x or whatever variable you use, you have to do parentheses a plus b. So you're expanding it, but then you're gonna have another expansion from there, or more algebra to do. But it's fun to think about the different see you around for more math and ASMR and math. Whatever we feel like around here. I'll see you very soon.